Donc toujours dans le cadre des soutenances des doctorants de la spécialité informatique, on passe à la soutenance de la candidate Novre, dont l'intitulé est IoT Network Dynamic Clustering and Communication for Surveillance UAVs. Donc, normalement, nos chers invités, surtout le professeur Farah, qui est toujours le dans le DAWA, et ainsi que les autres membres du jury. Donc, vous avez à peu près 30 minutes pour exposer votre travail.
Good evening, ladies and gentlemen. It is a great honor for me to stand before you today to present my PhD defense. Thank you to the esteemed jury for their invaluable feedback, gratitude to the audience for their support and engagement, and sincere appreciation to my professors for their guidance and mentorship. I am the candidate Robert Zaglia for the PhD degree in computer science, and I wish you find enjoyment and insights in my presentation. Allow me to provide you with a brief overview about the structure of my presentation, focusing on dynamic clustering and communication for surveillance UAVs, which is the central topic of my thesis. First, we will dive into the exciting realm of the Internet of Things. I will provide you with a brief overview about this transformative technology, highlighting its many benefits as well as the associated limitations we must overcome, from improving the efficiency of industrial processes to facilitating smart cities initiatives. The Internet of Things holds a big promises. However, we cannot ignore the pressing issues facing this technology. Following this, our attention will turn to drones, a powerful tools that have impact in various applications. But as with any groundbreaking tools, the drones come with their own set of challenges. So we will focus on the key issues and explore the complexities involved in deploying and operating them. And as every challenge is a new opportunity for innovation, I am excited to share with you the solution we developed to tackle these issues. And finally, we're gonna take our conclusion. So we will focus on the results of our research and draw insightful conclusions based on our findings. Let's start by the Internet of Things. So, the Internet of Things is a powerful technology that is shaping our world. But what does the combined expression Internet of Things mean? Let's break it down. The Internet refers to the classic connectivity we're all familiar with. It is the network that connects all devices around the world. But it is the term thing that raises our curiosity. So, what does a thing mean in this context? In the realm of the Internet of Things, a thing can be almost any object imaginable, extending far beyond the traditional smart devices, such as computers, phones, tablets, or more. Think of a door maybe, a road, or even a household. Items these can also be considered things in IoT ecosystem. But how do we integrate this seemingly inactivate object into our technology? The answer is to give them the connectivity and the power of sensing. By integrating sensors, we give ordinary objects the capacity and the ability to perceive and interact with their environment. And like this way, we are just building a whole system of Internet of Things. Now that we have established a basic understanding of what the Internet of Things includes, let's dive into some of its real-world applications. The great thing about the Internet of Things is its adaptability and diversity across industries and domains, from smart homes to industrial automation, from agriculture to healthcare. The IoT has permitted virtually every aspect of our lives, transforming the way we live, the way we work, and the way we interact with our environment. For example, in IoT or in the smart home space, the IoT devices enable seamless automation and remote control of household appliances, lighting, security systems, and even climate control. Imagine being able to adjust your temperature or lock your doors just remotely using your smartphone, or receive a real-time alert about the potential security breaches. All of these are just a few examples of how this technology is transforming our living space into intelligent, connected ecosystem. In the industrial sector, the IoT plays a critical role in optimizing processes, improving efficiency, and reducing downtime. Also, the Internet of Things extends far beyond our factories and homes. For example, in smart health, healthcare, we have wearable and remote monitoring systems enabling continuous health monitoring and early detection of medical problems, and also personalized treatment tailored by individual needs. We have also the agriculture, where the IoT-powered sensors and the drone are very efficient and powerful in helping farmers to improve their crop health monitoring and irrigation and improve their production. So, the architecture of the Internet of Things is structured into several layers. So we have sensors and devices layer that includes devices and sensors that collect data from their environment. We have the networking layer responsible of transmitting data between the devices and the servers, data processing layer where data is processed and analyzed, and finally the application layer utilizes these processed data to deliver services and functionality to end users for better decision making and automation. So if we go deeper into data processing layer, we find the cloud. So the cloud computing complements the Internet of Things by providing scalable storage and processing capacity, facilitating real-time data analysis and insights generation, enabling seamless integration across platforms and enhancing security compliance in IoT deployment. But the integration of the Internet of Things with the cloud computing has led to the emergence of cloud of things. A major limitation in IoT deployment is the bandwidth constraint. With the increasing number of connected devices or IoT devices generating a massive amount of data, especially in scenarios such as smart cities and industrial IoT application, the bandwidth can be exceeded, leading to network congestion and latency issues. So, the fog computing has emerged as a promising solution to tackle these issues by providing a decentralized connection by decentralized nodes of processing and storage units. But also, the fog computing has several limitations and benefits, so I mention of them: better security, reduced latency, improved efficiency, better privacy, and the most important one, which is the issue, is reduced bandwidth usage. For the disadvantage, I mention of them the complexity, geographical distribution, and the most important limitation of the fog computing is the limited resources. I mean here that the fog nodes they are limited of capacity in processing and storage, which can make an overload in any type of high traffic situation. So, the IoT devices or the Internet of Things comprises of many devices. Each of them is tailored to specific applications. The integration of these devices promises greater innovation and connectivity across all aspects of daily life. Drones, as a part of IoT ecosystem, possess unique characteristics of automation and mobility. So, setting them apart from the other devices, these features or these characteristics necessitate the specialized integration within IoT network. So, specialized integration strategy ensuring that a drone can operate autonomously and navigate dynamically within the IoT platforms and frameworks. So, let's explore these devices and learn more about them. For the application or the structure, the drones should be simple, lightweight, modular, and cost-effective, and should allow safe landing over harsh terrain and water. The drones were originally developed for military missions, but their use has expanded to many non-military missions or applications such as aerial photography, precision agriculture, environmental monitoring, and more, for example, surveillance, delivering, etc. So, the drones can be guided autonomously by remote control or both. They employ a host of advanced technologies that allow them to carry out their missions without human intervention, such as cloud computing, computer vision, artificial intelligence, machine learning, deep learning, and thermal sensors. So, for the pilot, Drones can carry sensors, target markers, offensive bombs, or electronic transmitters designed to destroy enemy targets. And finally, the efficiency. So drones have revolutionized efficiency in various industries, enabling rapid delivery in the delivery domain, precision agricultural monitoring in the agriculture, and swift aerial surveying in surveillance. But also drones have several or many limitations and, or I say, challenges. I mentioned of them: loss of connectivity, data redundancy in capturing data from the environment, complexity of collaborative missions between the drones and the base station. The battery life is so short because they consume a lot of energy. Noise pollution of the voice of the drones, and real-time decision-making issues because drones has no processing capacity or a lot of processing capacity and storage, so we should always use real-time decision-making like artificial intelligence. So here, two questions or problematic are posed for our research. The first one for the drones. How can we effectively harness the capabilities of drones to maximize their potential across various industries while simultaneously addressing challenges such as connectivity issues, data redundancy, and complexities in collaborative missions? The second question is about the fog computing limitation or issues. So our question is, what strategy can be implemented to prevent the overloading of fog nodes during periods of high traffic? To answer this question, we divided our research to 4 contributions. So the first contribution, a new drone recovery protocol is introduced aimed to preventing potential crashes by efficiently recovering misplaced drones. The second contribution introduces a dynamic fog computing-based mechanism to intelligently manage fog node states during saturation. The third contribution, we proposed a solution aims to enhance the efficiency of IoT-based drone network by dividing the fog area into smaller parts and optimizing data distribution among drones using concepts such as fog area division. And for the last contribution, this contribution presents a collaborative algorithm designed to improve multi-target surveillance and the tracking in drone environment. So let's start without any waiting our first contribution. So losing connection with a drone during a mission can be dangerous, especially in scenarios such as search and rescue, the current recovery systems cannot retrieve the drone or can only retrieve drones after it crashes, which can endanger mission success and data confidentiality. So the IoT network restricts devices connection to the authorized nodes only, which can lead to drone loss even if a valid network within range. A valid network, I mean here another fog node exists in the same area, but the drone cannot connect with this drone because they have no authorization to access to the network of the node. So the standard IoT architecture was proposed based on fixed devices, and the communication between device and the fog nodes cannot be interrupted due to the movement of devices outside the range of the fog. But the drones can always, that are mobile devices that can always fall out of the parent fog due to unexpected situations such as wind. So in that case, the drone cannot communicate outside of its fog parent, and the fog nodes cannot connect or communicate without cloud interconnection. So our proposed protocol for recovering lost in IoT environment involved 3 main elements: 1 role for the drone itself and 2 roles for the fog node. Let's begin by the drone. So The recovery algorithm is triggered when an interruption of connection is detected by a drone. There are three ways to reestablish connection. The first one is the drone tries to reconnect with its fog parent after a given time. If there is no response from the parent fog, the drone goes to the next way, which is broadcast a general attempt for connection to to find another fog node to receive its attempt. So the second method, based on finding any wireless network from nearby fogs to establish connection, even if the drone has no authorization to access. No response from any fog nodes indicates that the drone fell in a remote area. So as a final recourse, the drone can activate an adult mode and wait for assistance by another drone. So the rescue drone here, sent by the main fog, activate an ad hoc mode also and retrieve the lost drone in the extremity of the fog node only. So this strategy makes it possible to broaden the scope of the main fog only. And finally, after all of these steps, the drone should return to its area or find another connection or another network to connect. For the main fog role, so this algorithm is executed when a fog detects a failed connection within a drone. So in this case, the fog node takes on the role of the main fog. First, the fog node broadcasts its drone loss and trying to find another neighbor. So the appropriate fog here is selected to accept the communication with the lost drone. I mean here by the appropriate fog is the fog neighbor that can receive or accept the drone connection. Otherwise, the main fog, if there is no response, of course, that means there is no fog in that area. So otherwise, the main fog selects a drone among of its drones or devices and send it to the last known place where the connection was lost, and try to find the drone by an ad hoc network. And finally, try to retrieve the drone. The third role is the role of fog neighbor. So for the fog neighbor role, its mission is to catch the broadcast messages from the main fog and wait the connection attempt from the drone. So it's check the received information from the drones or devices and filter them according to the hash table or something else. So the goal here is to establish an indirect connection with the main fog until the drone is recovered. At this stage, the fog neighbor requests the connection from the main fog. After detection connection attempt from the drones and unsuccessful attempt from the main fog to reconnect with its drone. And finally, the fog neighbor requests the connection after finding a drone or devices from the fog neighbors and accept the connection and inform the rest by our election algorithm we made in our contribution. For the results, we proposed various scenarios with different number of drones and fogs. Each scenario was tested several times with random cases to get a different behavior. So based on our obtained results, we noticed that the system succeeded in recovering the lost drone in most cases with 86%. However, the recovery time is inversely proportional on the number of the fog nodes. So indeed, when the number of the fog nodes is high, there is a good chance that the drones fell in other fog area. Let's go to our second contribution. It's about the fog computing issue and the overload. So for computing as a promising solution, promising technology aims to bring IoT application closer to the edge devices, ensuring efficient real-time tasks completion. However, the limited resources of the fog nodes makes it sensitive to overloading or crashes, which have an impact of capacity and quality of service during high traffic periods. I mean here, for example, high crowded area or very crowded place. So our solution primarily focuses on dynamically monitoring the fog nodes' capacity and the adjustment of their states to accommodate in traffic volume through a new lightweight transition protocol. Our contribution is divided into two cases or two modes. So we have the default mode for the standard fog node operation, including receiving, storing, and processing tasks without any interruption, receiving data normally. The relay mode strategically activated during the overload, where the fog has no capacity to receive more data or more information. So it's temporarily suspending the processes and the processing and the storage of incoming tasks. So for the default mode, first of all, the proposed model allowed the two devices to send data without any conditions or limitation. For the default mode, the most important is the checking the capacity. So the fog node here is receiving data, storing, and processing without any limitation. But if the transmitted data makes the fog node full, the mode returns to the relay mode. Let's discover the relay mode. So the relay mode, this relay means that the fog was full and incapable to treat data. So the next step is depend to the checking the capacity until losing. So the fog node here suspend the receiving of data. So it's work like a transferring device between the higher level and devices until losing the half charge of data and return to the default mode again. That was our contribution and our solution. So for the results, the waiting time in the fog remained relatively stable, ranging from 4 to 5 seconds, regardless the number of devices. This indicates that the fog nodes were able to process the incoming data within consistent time frame. For the third contribution, in this contribution, we address the issue of repeated data transmission from the drones to a base station in IoT-based network, leading to the redundancy and the influence of the drones between each other. So the challenge includes limited bandwidth, network congestion, and increased cost. We propose an innovative solution to address the challenge of redundant data transmission in IoT-based network using drones. Our approach focuses on optimizing data or reducing data distribution and reducing the redundancy through fog area division and data load distribution among the drones. To reduce the redundancy, we divide the fog area into smaller parts. So, the fog area division algorithm involves several steps. The first one determine the size and the shape of the fog area, analyze the coverage requirements and identify regions of interest, calculate proximity between the drones and group them based on the proximity and regions of interest, and finally assign drones to specific fog area based on the proximity and coverage requirements. So, for the optimizing solution, the fog area division algorithm optimizes data transmission by promoting a collaborative and data sharing within each fog area, each part of the fog area. So the shot-by-shot capture method is designed to facilitate the coordination operation of surveillance drones in close proximity when only one drone is deployed in the destined area is captured, shot, and continuous rate of 5 shots per second, with each shot occupying a space of 5 kilobytes. So, however, in scenarios where 2 drones present or are simultaneously present within the same small part area, the method ensures the equal distribution and equal of the capturing shot between the drones. For the results, after applying the proposed solution for reducing data redundancy or transmission, so the data size is significantly reduced compared to the default operation without using any solution. This reduction in data size indicates that the proposed solution is effectively in optimizing bandwidth utilization. According to the finding, the suggested strategy has successfully decreased data size and maximize bandwidth usage, improving data transmission effectiveness. For the last contribution, a significant challenge arises when a single drone identifies multiple suspects as appears in our figure. So, leading to the inability to effectively target or track all targets simultaneously. To address this limitation, we introduced a collaborative algorithm designed to enhance multi-target surveillance and tracking in such environments. The algorithm fosters cooperation among the drones by dynamically selecting suitable assistant drone in the tracking process or in the tracking mission. So, for our proposed algorithm is centered around a collaborative approach wherein drones work in concert to track multiple suspects when a single drone's tracking capacity is exceeded. So, our approach is divided by suspect detection and information sharing, real-time collaboration and data fusion, and mission assignment and collaboration. So when a drone detects multiple suspects within its operational region, it collects relevant information about its suspects, including their position, image, or any other contextual data. This information is then transmitted to the base station for the analysis and decision making. The base station assigns a new tracking mission to another drone or assisting a drone. This mission involves tracking, maintaining visual contact with the additional suspect or target. The assisting drone receives mission details, suspect information, and the tracking objectives from the base station. For the results, the quantitative insights gained from these results demonstrate that our algorithm has a capacity to enhance multi-target tracking in IoT-driven surveillance the environment. So the algorithm's adaptability position is it has a promising solution for real-time deployment. So we focused on detection rate, which is the metric represented to percentage of correctly detected suspects, and was computed with the following equation, and the tracking precision calculated as the average Euclidean distance between the actual suspect position and their estimated position. This is for our last contribution. So as a conclusion, I can say the research contributes to strengthening drone integrity within IoT environment by addressing issues such as drone loss, high traffic situation, data protection, and collaborative mission. The finding offer practical solution to enhance the overall effectiveness and reliability of drones in IoT application. For the research challenges, we faced a lot of challenges, and the most important of them, the absence of standardized IoT and drone network simulation platforms that reflect the reality, the difficulty in development and testing a new idea without practical industrial or real-life scenarios for the drone use because it's not legal. And for our future work, the future of drones and IoT applications is very promising. FutureWorks aims to develop standardized platforms to drone mission assignment and configuration, focus on application in agriculture like agriculture and surveillance, bridge the gap between theoretical research and practical implementation of the use of drones, of course, and facilitate more effective and innovative application of drone technology. That's all for my presentation. Thank you for listening to me, and any of your questions, please.